Hey folks, there's a saying that nature abhors a vacuum. And it came to mind when I was watching a video that Andrei Linde made, a really fine video. It's actually spelled askegg. He used to make a lot of videos on YouTube, really terrific ones, and he still makes a few, but he used to be really out there a lot. And now he's busy working hard, and it's too bad because I really enjoy his perspective on things. And he was talking to a gal, a theist, was talking about, well, if God didn't make the universe, where did it come from? From nothing? And Andrew said, of course it didn't come from nothing. And it got me thinking about nothing. Because it turns out that science really doesn't allow for nothing, at least within our universe. Now the way that works is, if you just look at it from the standpoint of relativity, we found this thing called space-time. And it's no longer space, it's no longer time. They've been put together and they're not a grid. They're not a coordinate axis where we place things in time and in space. Space-time has become a thing. And essentially, it's hard to have nothing when you have a thing everywhere. Space-time can be warped and twisted and swirls around black holes. And it has different properties depending on how it warps. Essentially, it exists in a higher dimension in order to be able to warp. At least that's one way of explaining it. But that's not the really grand notion of why nature abhors a vacuum. I mean, where does the concept come? I mean, for instance, you could have a cup of tea and you could pour the tea out and you'd find out that the cup is now empty, or at least you think it would be empty. Maybe it has some air in there. Maybe a few particles of matter. But is it really, really empty? Well, according to quantum mechanics, it's not. Nor can it ever be. It's kind of like going to the beach, and you know where you kind of dig a hole in the sand near the water and it fills up with water? Well, that's how quantum mechanics works. It doesn't allow for nothing. Because everywhere, even in a so-called vacuum, are these things called virtual particles. Now, are they real or are they virtual? They're real, and I'll tell you why they're real. Because when we take measurements of space, assuming that they're there, they correspond to what we predict with the highest degree of precision and accuracy of any science known. That's right. Things work if those particles are there. If we remove them, the calculations come out wrong. There's something called the Casimir effect, where if we take a huge parallel plate capacitor, charge it up, it will change the properties of space in a way that will alter the speed of light. And it turns out that if those virtual particles aren't there, the math doesn't work. It doesn't match the predictions of nature. So what are these things? Well, virtual particles are things that pop out of nothing? No, out of space. But space isn't nothing. Time isn't nothing. And they do so because of the uncertainties inherent in quantum mechanics. It has to do with the Heisenberg uncertainty principle. The way quantum mechanics works is some things that are not forbidden have a probability of happening. And in quantum mechanics, if they have a probability of happening, they must happen. And as far as virtual particles happen, there are gazillions and gazillions of virtual particles everywhere. And the universe, life, and everything does not make sense without them. And what this means is that a vacuum isn't a vacuum. It has energy, it has properties. And if you try to scoop out all those particles, as soon as you did, there'd be more there. Okay, that was all very interesting, perhaps. But where is this leading? Well, the real question is, where does the universe come from? And my favorite, one of my favorites, probably my favorite Scientific American article ever, is by a fellow by the name of Andrei Linde. And he's from Stanford University, and he wrote a paper in Sci American 1994 entitled The Self-Reproducing Inflationary Universe, and I'm including it in the links. it's absolutely fascinating. And it basically says, because the question is, before the Big Bang, what was there? It basically has a model of the universe, a multiverse actually, as something like a fire. And the fire is growing and filling things up. That's the inflation of universes. Now, in universes, there's this inflationary phase that is going to be very great, and then there's an expansionary phase, which is going to be getting larger, but it doesn't occur at the same rate. And what happens is this fire is sort of growing, and that's a universe, universes, and then all of a sudden, due to quantum fluctuations that exceed a certain level, something's in my contact lens. Okay, now it's better. Quantum fluctuations that exceed a certain level, kind of like taking the thing on the toilet, you know, that little handle, and you push it down, you play with it, all of a sudden you reach a threshold, and all of a sudden the toilet is going to flush. Well, that's how this works. And so what will happen is the fire is burning, and then conditions suddenly change, and all of a sudden there's an explosion. And what happens is there is a tunnel formed to a new universe that expands rapidly. That's the inflationary phase. And as it expands, the properties of the universe are undefined. That's right. The universe, that fire that this other universe, these baby universes comes from, will have different properties. And they'll be fluctuating rapidly, and then they'll reach a point in which those properties will drop back down and become fixed. And that's how you get a new universe. And every new universe can make more universes in the same way. Now, to me, this is really cool, and I kind of explained it in such a way to make it exciting. But I got to tell you, this article has no mathematics in it. It's got pretty pictures, and I strongly recommend that you read it. It's cool science. I hope you enjoy it.